When light passes through a narrow opening, it will bend. How much it bends depends on the width of the opening and the wavelength. This phenomenon is known as diffraction. If you take a filter and you put a whole bunch of slits into it, then you have what we refer to as a diffraction grating. And what a diffraction grating does is it takes the incoming light and it breaks it up into its individual components. So all the frequencies that go into making that incoming light, they get spread apart. So you can clearly identify them as a result. And this is referred to as the spectrum. Okay? So the spectrum is, you might say, it's the set of all the individual frequencies that make up the incoming light. Now, ultimately what's happening is we're getting constructive and destructive interference. I don't want to get bogged down in the details, but that's how you end up getting the frequencies spread out like this. And I should say that this is referred to as a diffraction pattern or an interference pattern. Now, why is this important? If you take gas and you fluoresce it, it will emit a characteristic spectrum. This is known as an emission spectrum, and it turns out that these spectra are unique fingerprints. Okay? They are unique to each individual gas, whether it's carbon dioxide or hydrogen or helium, it doesn't matter. It's characteristic. And so if you have some gas out in space and it's fluorescing, it's going to give off this characteristic spectrum, and we can identify what it is based on that. Now, what can also happen is that you can have light from a star passing through gas, and it turns out gas will absorb those same frequencies that it would emit. Now, the star itself, I should say, is emitting essentially all the frequencies because it's giving off light because it's hot, not because it's fluorescing. It's giving off all the different frequencies because of all the thermal motion that's going on. So if we look at the spectrum of the star, we should see a rainbow. If we see some frequencies missing, then we know that's because there's gas between us and the star that's absorbing those specific frequencies. And so we can identify what that gas is, even though we can't see it. Now, why is that important? Why do we want to be able to do that? So you may be aware that in recent years, we have started discovering planets around other stars. We refer to these as exoplanets. And there was one spacecraft in particular, Kepler, that was really good at finding these planets. And what Kepler did is it would look at a star. In fact, it looked at hundreds of thousands of stars all at once. But what it's doing is looking at the brightness of those stars. And if the brightness dipped, okay, then presumably that's because something passed between us and the star. And if that dip appeared periodically, let's say every 6 months, then presumably it's because something is orbiting the star. And so, and that thing is probably a planet. If that planet has an atmosphere, then light from the star is going to pass through that atmosphere. And as a result, some of those frequencies are going to be absorbed by the atmosphere. So if we take very careful measurements of the spectrum of the star, we can see those frequencies disappear. And then we can identify what's in the atmosphere of that planet. You know, and people talk about wanting to go to other solar systems, wanting to find other planets that we could potentially inhabit. So obviously we want to find oxygen around some of the planets. So this is one of the potential benefits of taking these spectra, looking for, you know, the planets that have an atmosphere that is conducive to life from our planet. Now, let me just say a brief side note. This idea here of being able to look out in space and identify what is out there just based on looking at the spectrum that we see of some gas or whatnot is truly fascinating. It means that we can identify, for example, if there's water in some cloud of gas or on another planet potentially, that's hundreds of, if not thousands of light years away from us. However, for whatever reason, if you go to the airport, they are not able to tell you if there is water here in your water bottle. They can't tell you that, you've got to pour it out. But we can tell if there is water in another planet, its atmosphere, or in some gas cloud that, again, is light years away. Truly amazing. Now, I want to now switch over and show you actually the spectra, how the diffraction grating works and how we're able to see the spectrum from some gas that is fluorescing. This is hydrogen gas that is fluorescing, and if I hold up the diffraction grating, we're looking straight through the diffraction grating, and officially what we're seeing is the 0th order. This is the undeflected incoming light. But if I move this off to the side, I'll see some of the light that's been bent. Here we go. And we can see the spectrum of light. These are the three main components that make up the light from the hydrogen gas. We see the purple, or you might call it violet line. We see the teal line, maybe blue, but teal is what it looks like to me. And we see the red line. And one thing I want to note is that it appears to the right, but it also appears to the left. And the light gets bent both ways. Now, as I said, this is the spectrum, and it's the first order. Okay, and it's the first order because it's the first time we are encountering it as we move to the right. Or when we go to the left, same thing, that would be the first order. If you keep going, you will see a second order. I can't do it here, the camera won't pick it up. But if we went again, we saw the spectrum repeat, that would be the second order. If we saw it repeat again, that would be the third order. And again, that's as we're going to the right. As we're going to the right, if I keep seeing the light, you know, it seems like the teal is just barely showing up there. I don't know if that's coming through. But if you keep going, then we'd see the second order, then we'd see third order, and so on. There is a limit to how many orders you see. So this is the formula for diffraction grating. Sine of theta sub m equals n times m times lambda. Lambda, of course, is the wavelength. Big N, right here, this is the number of lines per unit distance. So lines per meter, lines per centimeter, lines per millimeter. It's the linear line density on the diffraction grating. If you look in other textbooks, they usually write this formula like so. Sine of theta sub m equals m lambda over d. And you can see that looks different than ours. It turns out that n equals 1 over d. I prefer to express the formula in this way because when you look at a diffraction grating, this is the value that is stated on the diffraction grating. They tell you n. They don't tell you d. They tell you the linear line density. So that's why we use this formula in this course. Now m, which is the order, and is directly related to theta sub m. Let's talk about that. So you have incoming light that is incident on the diffraction grating. Some of that light will pass through undeflected. This is the 0th order. Now we're going to assume all of this light is the same wavelength. Okay? So some of that light gets bent various amounts. And the light that is right here on this red line, whether the top one or the bottom one, that is the first order. That is m equals 1. And it's the first order because it's the first line, or the first line next to the 0th order. So that's why it's the first order. Then the purple lines, they represent the second order. And there can be third and fourth and fifth orders. I'm only drawing up to second order. I also want to mention, by the way, that I've got these lines as different colors. That is not reflective of how they actually look, the frequency of the light. I'm putting different colors so we can easily identify the different orders, that's all. Now, the angles from the 0th order to the first order is theta sub 1, whether we're doing the top or the bottom. From the 0th order to the second order, it's theta sub 2. This angle here, theta sub m, is always measured from the order you're interested in to the 0th order. So for the 0th order itself, that angle is just 0. Okay? But for theta 1, okay, so I'm at my first order line and I have to measure over to the 0th order. For theta 2, I have to measure from here to the 0th order. If I had a theta 3, if I had a third order, I'd have to measure from that third order all the way over to the 0th order. And I should mention, there's a practical limit to how many orders there can be. because the biggest angle you can have is 90 degrees. So that's going to put a limit on what M can be, the largest it can be, how many orders we can actually have. But this is the gist of it. Pretty straightforward formula. Not the simplest one we've had, but still pretty straightforward. You just need to be clear on really what the idea of an order is. You need to have that straight and what these angles are. And then it's just a matter of plugging and chugging.